Now let us discuss the properties of limits that we can use to evaluate limits. The limit of a constant as x approaches c is just equal to that constant. And this is true for any constant. Say, for instance, the limit of 3 as x approaches 2 is just equal to 3. And the limit of pi is a constant number approximately equal to 3.14 as x approaches 0 is equal to pi. It's equal to the given constant here. And also the limit of x as x approaches c is just equal to c. That means you just replace x here by c. And also, if you have two functions f and g, and the limit of the two functions as x approaches c both exist, and it's equal to L for the limit of f of x as x approaches c, and for the limit of g of x as x approaches c, it's equal to m, then we say that the limit of the sum or difference of the two functions f and g is just equal to the sum and difference of the limits. In other words, you can distribute limit over addition or subtraction. And the answer is also just the sum or difference of the limits. And with that, we can say that the limit of x plus 3 as x approaches 2, for instance, is just equal to the limit of x. So you distribute the limit over addition. So it is equal to the limit of x as x approaches 2 plus the limit of 3 as x approaches 2. And since the limit of x as x approaches 2 is equal to 2, because you can just replace the x here by 2. And the limit of a constant is just equal to this constant. So we have 2 plus 3, and that is equal to 5. And also, the limit of constant times a function is just equal to the constant times the limit of the function as x approaches c. In other words, you can take out the constant and just evaluate the function. So therefore, the limit of k times f of x as x approaches c, since the limit of f of x as x approaches c is equal to L, then this is just equal to k times L. Now, for instance, if we want to evaluate the limit of 3x as x approaches 2, then what you can do is you can take out the constant. So using this property here, you take out the 3 outside of the limit. So you have 3 times the limit of x as x approaches 2. Now using the property here, property number 2, the limit of x as x approaches 2 is equal to 2. So this is just equal to 3, which is this constant here, times the value for the limit here, the limit of x as x approaches 2, which is 2. And that gives us 6. And also the limit of the product. The limit of the product is equal to the product of the limits. So that means if you want to evaluate the limit of f of x times g of x as x approaches c, you can get the value by distributing limit over multiplication. So you get the limit of f of x first as x approaches c, and then multiply that to the limit of g of x as x approaches c. Now the limit of f of x as x approaches c is given to be equal to L, and the limit of g of x as x approaches c is equal to m. So therefore, this is just equal to L times m. So therefore, we can apply this to this example, the limit of x squared as x approaches 2, for instance. So the limit of x squared is also the same as, you know, that x squared is equal to x times x. So therefore, you can think of this as limit of x as x approaches 2 times the limit of x as x approaches 2. So the limit of x as x approaches 2 is 2 times this one here. The value is also equal to 2. So the answer is equal to 4. And also, the limit of the quotient is equal to the quotient of the limits. So when you are finding the limit of f of x divided by g of x, you can evaluate that by evaluating first the limit of f of x, and then evaluate the limit of g of x as x approaches c. Now, since this is given to be equal to L, and the limit of g of x as x approaches c is equal to m, so therefore the limit of f of x over g of x as x approaches c is equal to L over m. And lastly, the nth root of, if you want to take the limit of the nth root of f of x as x approaches c, you can evaluate this by taking the limit inside the square root. And that means the limit of the nth root of f of x as x approaches c is equal to the nth root of the limit of f of x as x approaches c. Now, since this is given to be equal to L, so the limit here is just equal to the nth root of L, provided that L here is greater than 0, or n is odd. Now with that, we can extend this property to this example here. We have limit of x squared. So as an alternative, you can evaluate the limit of x squared, because this n here, this one will also hold true even for the exponent. So this means you have a fractional exponent here. So you can extend that to exponents that are not fractions. For instance, the limit of x squared. So instead of evaluating this the way we evaluated it here, you can also evaluate it using the property number 8 as limit of, you take it inside the power. So limit of x, get the limit of x first as x approaches 2, and then you square that. And you get the same result. Now the limit of x as x approaches 2 is equal to 2. And raise that to 2, which is 4, which is exactly what you got in the previous example. Now let us apply the properties of limit to evaluate the limit of x squared minus 3x as x approaches 2. So to do this, we can distribute limit first over subtraction. We have limit of x squared as x approaches 2 minus the limit of 3x as x approaches 2. And this is also equal to so this part here is also equal to the limit of x as x approaches 2 quantity squared. So you take the limit first of this variable. Minus, you take out the 3 here. So you have 3 limit of x as x approaches 2. Now the limit of x as x approaches 2 is just equal to 2. You just plug into x. So this means this is equal to 2 squared minus 3 times 2. That gives us 4 minus 6. And that's equal to negative 2. Now, if you notice from this example, when you try to evaluate the limit of a polynomial expression like this, all you need to do is just evaluate or plug in the value of x here to the expression. And that's what we found here. So we apply all these properties here, and then we arrived at this step here, which is the same as just plugging in values to x, plugging in this x value to x. So that means you can generalize this, that when you are trying to evaluate the limit of a polynomial function, all you need to do is plug in the value of x here to the expression, and the result is the limit. So now let's formalize that by using this theorem here. If you have f as a polynomial function, the limit of f of x as x approaches c is just equal to the value of the function evaluated at c. And similarly, if you have a rational function, that limit of the rational function is just equal to the value of the rational function at x equals c, provided that the denominator is not equal to 0 at x equals c. Now let's apply that to the following examples here. So this theorem says that if you are to evaluate a limit, all you need to do is plug in or substitute the value of x here to the variables here. So the limit of 2x to the fourth minus 3x squared plus 1 is equal to 2 times 2 to the fourth minus 3 times 2 squared plus 1. And this is equal to 2 times, now 2 to the fourth is equal to 16. So 2 times 16 minus 3 times 2 squared is 4. 2 times 2 plus 1. And this is equal to 2 times 16 is equal to 32 minus 12 plus 1. 32 minus 12 is 20 plus 1 is 21. Now letter B, let's find the limit of the expression here. So for cube root of this polynomial function, we know that we can take the limit inside the cube root. So this is the same as the cube root of the limit of 2x to the fourth minus 3x squared plus 1 as x approaches 1. Now this is just a polynomial expression, so we can evaluate the limit here by just plugging in 1 to the expression. So this is cube root of 2 times 1 to the fourth minus 3 times 1 squared plus 1. Now 2 times 1 to the fourth is equal to 1. 1 squared is also equal to 1. So we have 2 times 1 is equal to 2 minus 3 times 1, which is equal to 3. So negative 1. 2 minus 3 is negative 1 plus 1 is equal to 0. Cube root of 0 is equal to 0. Now, as you see here, this is also similar to just evaluating the expression here at x equals 1. So in other words, we see a technique here in evaluating limits. To evaluate the limit, we will first have to attempt to substitute the value of x in the given expression and simplify it to find the limit. Now let's look at the particular examples here. So when we evaluate limit, all we need to do is substitute or plug in value of x here. So therefore, the limit of x to the fourth minus 2x plus 3 as x approaches -1 is equal to -1 to the fourth minus 2 times -1 plus 3. And then simplify. -1 to the fourth is +1. -2 times -1 is +2 plus 3. And then simplifying this gives you 6. Similarly, for letter B, to evaluate the limit here, you just plug in, replace x by 2. So this is equal to the square root of 3 times 2 squared minus 6. Now, 2 squared is 4 times 3 is 12 minus 6 is 6. So this is equal to the square root of 6. And for letter C, you do the same thing. You replace x here by -2. So you plug in, you substitute the value of x here to the x's here. So you have -2 squared divided by -2 squared plus 1. And -2 squared is 4. -2 squared means -2 times -2. So that's 4 plus 1 is 5. So the answer here is 4/5. Now let us consider the case where we are given a piecewise function and we are asked to evaluate the limit of the functions at different values of x. So for instance, letter A, we want to find the limit of the function as x approaches -2. Now, you look at where you find -2 in the intervals here. So our function is defined as x squared plus 1 if x is less than 2, and it is equal to x minus 1 if x is greater than or equal to 2. Now, -2 is on this interval, that is on the interval less than 2. So therefore, to evaluate the limit here of the function, we will replace f of x by the definition of the function in this value here of x. So as x approaches -2, you find that in this interval. So therefore, the function there is equal to x squared plus 1. And then you write as x approaches -2. And after that, you can plug in or you can evaluate this function here at x equals -2. So this is equal to -2 squared plus 1. -2 squared is 4 plus 1 is 5. So the limit of the function as x approaches -2 is 5. Now similarly, when you find the limit of f of x as x approaches 3, you look at this value here and locate which interval you will find x equals 3. Now x equals 3 is in or within this interval here, within x greater than or equal to 2. So 3 is greater than 2. So therefore the function is defined as x minus 1. So therefore we write this as the limit of x minus 1 as x approaches 3. Then after that you plug in x here, or you evaluate the function at x equals 3. And that is 3 minus 1, which is 2. Now for the last example, we want to find the limit of the function as x approaches 2. Now notice that this number here is the endpoint of the intervals. So 2 is in here. That means that the limit at the left-hand side of 2, if you look at the function or if you approach the function at x equals 2 from the left, meaning the values of 2 coming from the left side of 2, you replace the function, this function here, you replace f of x by, left side of 2 is less than 2, so you replace that by x squared plus 1. And then you evaluate the limit at x equals 2. So this one, the negative sign here indicates the direction where the x values are coming from. So this one means it is coming from the left side of 2. And then when you plug in, you do the same thing. You just evaluate the function at this value of x here. So you have 2 squared plus 1, which is 5. Now, if you look at the limit of the function as x approaches 2 from the right, that means right side of 2, you replace f of x by the definition of the function at the right side of 2. Now at the right side of 2, the function is defined as x minus 1. So you have x minus 1 here when x approaches 2 from the right. And then you plug in. So you have 2 minus 1, which is equal to 1. Now, notice that we get 2 different values here. The function approaches to 5 when x are coming from the left side of 2. And the function approaches to 1 when the x values are coming from the right side of 2. So therefore, this implies that the limit of the function as x approaches 2 does not exist.